Today we will discuss about the error control coding system, subject of the principle of communication. So what is the error control coding? So there are some contents. First one is error correction codes, channel coding, and second one classification of error, and next error detection technique, error correcting technique, drawback of coding technique, classification of error correcting codes, type of error controls, type of linear block codes, and definition related to codes. Overview of error control coding technique, automatic repeat request ARQ, forward error correction FEC technique, transmission errors, and power and bandwidth channels. Next, error detection methods and cyclic redundancy check. So, in introduction of the coding theory, coding theory is one of the most important and direct application of information theory. It can be subdivided into source coding theory and channel coding theory. So using a data of information theory, quantify the number of bits needed to describe the data, which is the information entropy of the source. Coding theory, sometimes called algebraic coding theory, deals with the design of error correcting codes for the transmission of information across noisy channels. It makes use of classical and modern algebraic technique involving finite fields, group theory, and polynomial algebra. It has also connections with other areas of discrete mathematics, especially number theory and the theory of experimental designs. So this is the introduction about the coding theory or information theory. There are two aspects of coding theory types. First one is the data comparison or source coding. Second one is the error correction or channel coding. So these are the two types of the coding theory. First one, the data compression of source coding. There are two formulations for the compression problem. First one is the less data compression. The data must be reconstructed exactly. Second one, lossy data compression. All allocate bits needed to reconstruct the data within a specified fidelity level measured by a distortion function. So this subset of information theory is called rate distortion theory, RDT. Error correcting codes. What is the error correcting code? So while data compression remove as much redundancy as possible, and error correcting codes adds just the right kind of redundancy. Error corrections needed to transmit the data efficiently and faithfully across a noisy channel. Next, what is the classification of codes? So there are classification in three types. First one is error detecting, second one is error correcting, and third one is error correcting technique. So these are the classification of codes. Next, classification of errors. So first, content errors, error in the content of message introduced due to noise during transmission. Second one is flow integrity error or missing block of data, data lost in network of data delivered to wrong destinations. So that is the classification of about the errors. What is the error detection technique? So in error detection technique, first one is the parity checking, and second one checks some error detecting. Third one is the cycling redundancy check CRC. Next, error correcting techniques. So error correcting techniques are first based on generation of code words at the transmitter. Second, coded words contains the data bits and check bits. So there are some drawback of coding techniques. First one is drawback of coding technique is that in increased transmission bandwidth because of addition of extra bits. So this is the first drawback of coding technique. Second drawback is increased complexity of communication system. So classification of error correcting codes, there is code word length in n bits, and k is the message bits here, and n minus k is the parity bits here. So total sum of message bits plus n minus k parity bit is the code word length. So here in this diagram, a message signal empty is applied to the encoder with input response ST. So the output of this encoder is the encoded output empty multiply ST. So output of the encoded is the empty multiply ST. ST is the transfer function of the encoder here. There are some another classifications. First one is linear codes and second one is non-linear codes. In linear codes have the unique property that when any two codes words of linear codes are added in a module 2 adder, third code word is produced, which is also a code, which is not the case for non-linear codes. There are some type of error control. So first is automatic request for retransmission ARQ. The receiver can request for retransmission of complete or part of message requiring additional channels called feedback channels. So additional channel is the feedback channels. Second is forward error correction FEC. In FEC, no feedback channel is available here. So in coding theory, a linear code is an error correcting code for which any linear combination of code word is also a code word. Next, linear code are traditionally partitioned into block codes and convolution codes, although turbo codes can be seen as a hybrid of these two types. Linear codes allow for more efficient encoding and decoding algorithms than other codes. In coding theory, block codes comprise the large and important family of error correcting codes that encode data in blocks. Examples of block codes are Reed Solomon codes, Hamming codes, Hadamard codes, expander codes, and Gole codes, and Reed-Muller codes. These examples also belong to the class of linear codes, and hence they are called linear block codes. There are different types of linear block codes. So first one is cyclic codes or Hamming codes. Second one is repetition codes, and third is parity codes, and fourth is polynomial codes or BCH codes. Next one is Reed-Solomon codes, and next is algebraic geometric codes, and also Reed-Muller codes, perfect codes, single parity check bits codes, and repeated codes, and Hadamard codes, and also extended codes, and last Gole codes. So these are the linear block codes types. The important definition related to codes. The code word is the n-bit encoded block of bits. It contains message bit and parity or redundant bits, and block length. So the number of bits n after coding is known as block length. And what is the code rate? So the code rate is defined as the relation of the number of message bit k to the total number of bit n in a code word. So code rate is the k per n equal to k per n. What is the code vector? N bit code word can be visualized in an n-dimensional space as a vector whose elements or coordinates are bits in the code word. So Hamming distance, what is the Hamming distance? In Hamming distance, it is the distance between the two codes expressed in the number of locations in which their respective elements differs. Hamming weight of a code word Wx, it is defined as the number of non-zero element in the code words. Next one is the what is the code efficiency. So code efficiency is defined as the ratio of message bit to the number of transmitted bits per blocks. Code efficiency is equal to that of code rate. What is the minimum distance? So minimum distance is defined as the smallest Hamming distance between any pair of code vector in the code. So these are the some important definitions related to the codes. In this block diagram, that is the overview of error control coding technique. So here error control coding technique divide into three parts. One is the forward error corrections. Second one is the automatic repeat request. And third one is the hybrid ARQ. Also, forward error correction divided into two parts. First one is concealment error and second is linear error correcting codes, and again linear error correcting codes divided into the two parts. One part is the convolution codes, and that is also divided into three parts. One is the self orthogonal codes, second is the trial and error codes, and third one is the recursive systematic codes, and also linear error correcting code divided into block codes, and block codes again into BCH codes, and BCH code divided into two types. First one is read Solomon code or non-binary codes. Second is the Hamming codes or binary code. So this diagram shows the overview of error control coding techniques. Error detection and correction capabilities. So there are some description. First one is detect up to error forward. So expression is that distance, minimum distance greater than equal to s plus 1. Second description is correct up to 1 t error forward. So minimum distance will be greater than or equal to 2t plus 1. Next description is correct up to t error and detect s greater than t error forward. So expression for the minimum distance will be greater than or equal to t plus s plus 1. So there are error detection and correction capabilities. Yes. Next, automatic repeat request ARQ. So what is the ARQ? Here, when an error is detected, a request is made for retransmission of signal. A feedback channel is necessary for this transmission. It differs from the FEC system in the following three aspects. So first aspect is less number of check bit, parity bit are required, increasing the ratio for NK block codes. Second aspect, additional hardware to implement feedback path is required here. And third aspect is that what rate at forward transmission need to make allowance for backward repeat transmission. So these are the some three aspects for the FEC systems. Next, what is the operation of ARQ? For each message signal at the input, the encoder produces code words which are stored temporarily at encoder output and transmitted over forward transmission channel. At the destination, decoder decode the signal and give a positive respectively in case no error and error is detected. On receipt of NAK, the controller retransmit an appropriate word stored in the input buffer. So in this block diagram, here is the message input applied to the encoder, and encoder encode this input message and apply to the input buffer and controller. The buffer and controller also a signal applied here from the return transmission channels, and the output of buffer and controller to applied forward transmission channel, and after of the forward transmission channel the signal is applied to the detectors, and after the detecting the signal, this signal is applied to output buffer and controller. So this is the operation of ARQ. The bit rate of return transmission involving ACK oblique NAK transmission is lower compared to bit rate of forward transmission, decreasing the probability error in return transmission to such a small value that it may be neglected. So there are exist three type of ARQ system. First one is stop and wait ARQ. Second system is go back ARQ. And third system is selective repeat ARQ. So there are three types of ARQ systems. Next, forward error correction FEC technique. So what is the forward error FEC technique? FEC technique is a digital modulation system where discrete source generates information in binary form. The channel encoder accepts these message bits and add redundant bits to them, leaving higher bit rate of transmission. So channel encoders use the redundant bits to check for actually and erroneous transmitted message. So in this diagram, there is a discrete source, and this source output applied to the channel encoder, and also a message channel is also applied to the channel encoder. The after the encoding, the channel encoder output applied to the discrete channel, and in this discrete channel also a mixing of noise from outer side, and the output of this discrete channel is again applied to the channel decoder, and here the signal is decoded by the decoder network, and output of the this decoder is the applied to the destination, which is the output of the discrete source signal, which is transmitted through the different networks by the encoder network, discrete channel, and decoder channels. And so this is the explanation about the FEC technique in the form of block diagram. Now we discuss about the transmission errors. So there are two types of transmission errors. First one is random error and second one is the worst error. So in random errors are those that occurs in a purely random manners. DCH codes are useful in dealing with this sort of errors. What in worst errors occur in form of bunches and are not independent. Convolution codes are no effective for this sort of errors. So fire codes which form a subclass of cyclic codes are effective in these types of errors. So interleaving is a technique. What is the interleaving? So interleaving is a technique which is used in alternative for correcting worst errors. So this is the interleaving technique. What is the power and bandwidth of the channel? So basically bandwidth is the difference of the two frequencies, high frequency minus low frequency, that is the bandwidth, or bandwidth is the path of communication. So let the input data rate be B bits per second. The FEC encoder convert this into coded word at a rate of bit per rate, where R stand for information rate. So rate is the B oblique R, bit per R. So R stand for information rate. Here the M symbol modulators convert the encoder output into M possible symbol constellation having the symbol rate. So bit per KR baud at the output. Minimum system bandwidth required for successful transmission is the bandwidth efficiency is. So M equal to number array for TSK. So band limited channels. What is the band limited channels? They have finite fixed bandwidth signals requiring larger bandwidth, therefore cannot be transmitted over these channels without distortion. Telephonic lines comes under band limited channels. So telephone's line is the one examples of the band limited channels. Next, power limited channel. So what is the power limited channels? In power limited channels, they have limited power associated with them but have large bandwidth. Satellite, for example, satellite channels. This is the examples of power limited channel is the satellite channels. It is therefore possible to accommodate FEC even with increased data rates. So what is the error detection methods? Error correction is only possible if error are detected in the code word. There exist many methods for error detection. The most popular methods which are here. So these are three types. First error detection method is the parity checking method. Second is the checksum error detections. And third one is the cyclic redundancy check or CRC method. So these are total three methods for error detection, which are most popular. So first method is the parity checking. So here an additional bit is appended with the existing message bits known as the parity bits. As a result of addition of this extra bit, the resultant word now will have either even or odd parity. For example, number of 1 in the code word will be either even or odd. If it is known that the parity of the received message is always going to be even or odd, as the case may be, and if the received signal does not tally with the expected result, the presence of an error is detected. The limitation of this method is that it can only detect odd number of errors, and also it is unable to locate the position of the error. So this is the limitation of this parity checking methods. Next one is checksum error detections. In checksum error detections, for worst errors, parity check method is not useful. Here then the checksum method is applied. Here the checksum is transmitted along with every block of data bytes or 8 bits. Here an 8-bit accumulator is used to add 8 bits of a block of data to find the checksum, and the carries in the MSB are discounted while finding the checksum byte. Transmission of data byte is followed by transmission of checksum byte, which is regenerated at the receiver separately by adding the received byte. So after comparison with the transmitted byte, if results are identical, it is concluded that no error has occurred, otherwise there exist errors. As byte of checksum is transmitted, there is 255 to 1 chance of detecting random errors in this checksum error detection technique. So next one is the cyclic redundancy check CRC technique. The concept of parity checking can be extended from detection to correction of single error by arranging the data block in rectangular matrix form. So this will lead to two set of parity bits. First one is longitudinal redundancy check LRC, and second one is vertical redundancy check VRC. So there will be two set of parity bits here, LRC and second is VRC in the cyclic redundancy check technique. Now in longitudinal redundancy check, in LRC, one row is taken up at a time and counting the number of ones. The parity bit is adjusted to achieve even parity. Here for checking the message block, a complete character known as block check character BCC is added at the end of the block of information, which may be even or odd parity. So that is the LRC technique. Next one is vertical redundancy check, VRC. In VRC, the ASCII code for individual alphabets are considered arranged vertically and then counting the number of ones. The parity bit is adjusted to achieve even parity. So a single error in any bit will result in a non-correct LRC in the row and a non-correct BRC in the column. The bit which is common to both the row and column is the bit in error. So the limitation is though it can detect multiple error, what is capable to correct only a single error. As for multiple errors, it is not suitable for locate the position of the errors. One in the square box in the next table is the bit in error, as it is evident from the erroneous result both in the LRC and the BRC column. So here is the some characters, 7-bit ASCII codes message bits here, and also LRC bits, that is 1100000001, and different bits B1, B2, B3, B4, B5, B6, B7 here, and this is the CRC technique explanation in the form of BRC and ASCII code for the individual alphabet are considered arranging vertically and then counting number of one. The parity bit is adjusted to achieve even parity. Now we will discuss about the source coding theorem. So what is the source coding theorem? In source coding theorem, the theorem described thus far establishes fundamental limit on error-free communication over both reliable and unreliable channels. In this section, we turn to the case in which the channel is error-free but communication process itself is lossy. So under these circumstances, the principal function of the communication system is the information compression. The average error introduced by the compression is constant to some maximum allowable level D, we want to determine the smallest rate at which information about the source can be conveyed to the users. So this problem is specifically addressed by a branch of information theory known as the rate distortion theory. In this block diagram, there is the information source, which is information source to apply the output of information source to the encoder, and encoder again applied the output of encoder to the channel, and channel applied this signal to the decoder, and decoder applied to the information users. So this is the communication system in which different networks are information source, encoder, decoder, and channels. So encoder encode the information source, and again decoder decoding the information source from to original information source. So let the information source and decoder output is defined by the finite assemblies AZ and BZ respectively. The assumption now is that the channel of the figure is error-free. So a channel matrix Q which relates Z to V in accordance with V equal to QZ can be thought of as modeling the encoding decoding process alone. Because the encoding decoding process is determined where Q determines a artificial zero memory channels that models the effect of the compression and decompression. Each time source produce source symbols, so it is represented by a code symbols, that is Q, and then decode a output symbol H with probability, addressing the problem of encoding the source so that the average distortion is less than D. A non-negative cost function called a distortion measures can be used to define the penalty associated with reproducing source output with decoder output. The output of the source is random, so the distortion also is a random variable whose average value denoted by dq is. So the notation dq emphasizes that the average distortion is a function of the encoding decoding procedure. So qd equal to qd q less than or equal to d, and rate distortion function will be rd equal to minimum lzv and equal to q equal to qd. If d equal to 0, then rd is less than or equal to hz. So we simply minimize izv by appropriate choice of Q subject to the constant. So Q is greater than or equal to 0 and dq equal to d. The above equation are fundamental properties of the channel matrix Q. These are the some reference books for this topics. And there are some important multi-choice questions. Question first, the capacity of Gaussian channel is option A, C equal to 2b s plus n upon n bit per second. Option B, C equal to v square s plus n s upon n bit per second. Option C equal to b s 1 plus s upon n bit per second. And option D, C equal to v into 1 plus s upon n into 2 bit per second. So here the capacity of Gaussian channel is the C equal to b into s upon n bit per second. So correct answer is here option C. Next, for an equally likely message, the average amount of information h is option A h equal to log of 10 m, option B h equal to log of 2 m, option C h equal to log of 10 m square, and option D h equal to 2 log of 10 m. So correct answer here option B h equal to log of 2 m. This is the information amount. And next, the channel capacity is the maximum information transmitted by one symbol over the channel. Option B, information contained in a signal. Option C, the amplitude of the modulated signal. Option D, all of the above. So correct answer here, option A. Channel capacity is the maximum information transmitted by one symbol over the channel. Next, according to the Shannon-Hartley theorem, option A, the channel capacity becomes infinite with infinite bandwidth. Option B, the channel capacity does not become infinite with infinite bandwidth. Option C has a trade-off between bandwidth and signal to noise ratio. Option D, both B and C are correct. So here option correct is the option D. Both B and C are correct according to the Shannon-Hartley theorem. Next question, the negative statement for Shannon theorem states that option A, if R is greater than C, the error probability increase toward unity. Option B, if R is less than C, the error probability is very small. Option C, both A and B. Option D, none of these. So correct answer is here option A. For M equally likely message, M is very greater than 1. If the rate of information R is greater than C, the probability of error is option A, arbitrary small, close to unity. Option C, not predictable. And option D, unknown. So correct answer here is option D, close to unity. The channel capacity according to Shannon's equation is option A, maximum error-free communication. Option B, define the optimum systems. Option C, information transmitted. Option D, all of the above. So correct answer is the D. So these are the some multi-choice question that is the very important for clear the concept of this topic. So thank you very much.